Hey guys, welcome to today's lesson. We're looking at the volumes about the x and y axis. This is the last video or the last new concept to learn within the integration module of the 2-unit HSC mathematics. It is a little bit challenging, but it's primarily based on the information that you've already learned about areas underneath a curve. But instead of looking at areas, we're looking at volumes. I'm just going to look at briefly, and you can do it about the x or the y axis. So I'm going to start looking at, let's look at a parabola like that as such. So that's something in the form of x equals y squared. And we're going to look at the volume of this about the x-axis. Now, what does volume about the x-axis mean? Now, picture that this parabola, I guess, is rotated around, that means around this axis here. It's twisted around. And what actually happens as it rotates around, it creates this sort of, kind of like a cone, sort of, I often talk about as a shell or, this sort of object. But again, it's hard. You need to sort of visualize this parabola turning around that x-axis, and as it does that, it creates this sort of circle shape here. Now, this would be rotating about, I'll say, the x-axis, and likewise, we could look at a graph of y equals x squared, like this one, for example. And this one would rotate about the y-axis, okay? Because if I rotated that one around that y-axis, then think of that y-axis in this case being the center pole, and it's spinning around that pole. It would sort of create, again, this sort of, I guess this semi-spherical sort of shape as it's spinning around and around and around. That would be about the y-axis. Now that's important, and because it's to find the volume of these two types of questions, I guess. We have to learn a rule. Okay, and the rule is quite similar to what we've done previously, but again, slightly different. Now, I'm not going to go through exactly where the rule comes from, how to get the rule. If you want to know that, certainly I can make another lesson on that. But just a very brief sort of explanation. They take this circular disc that's kind of been made here, and they take another circular disc sort of through here. And they look at this shape here, which kind of looks like an odd case sort of cylinder. And the volume of a cylinder is pi r squared times height. Now, if you think about this amount here, if I looked at the radius, let's say the radius of y, let's say the radius is there is the length of y. Let's call that our h. We'd say the volume equals pi times y squared times h. If we took an infinite amount of these discs and took the sum of those, it would look that h would approach 0, okay, and would leave me with volume equals pi times y squared. Now again, that's not going to make too much sense to you. That doesn't need to happen, okay? What needs to happen is the two formulas that you need to know. So when we're rotating about the x-axis, the formula you need to remember is this: volume equals pi times the integral of y squared dx. Okay, if I'm rotating about the y-axis, we want to know the formula is volume equals pi times the integral of x squared dy. Now, how did I go from the formula for the pi times y squared to this bit? Well, I guess the y squared part is kind of looking at your area, I guess, and our area comes from the integral. All right, the end underneath the curve is integral. So I've got the integral of y squared, and then we've got the pi at the front, which you can have, that's no dramas. Likewise, pi at the front of integral of x squared dy. So what you need to remember is when you're finding volume, that instead of it being the integral of x dy or y dx, etc., like we've been doing before, it's pi times integral of y squared, or pi times integral of x squared, depending if you're rotating about the x-axis or depending if you're rotating about the y-axis. It is very important which of those two you sort of look at. Again, it is a bit confusing, so apologies, but you will sort of get the hang of it as you go through these tutorials. Okay, so I'm going to look at the first question here, which says, find the volume of the solid of revolution formed when the curve x squared plus y squared equals 9, which is a circle, is rotated about the x-axis between x is 1 and x is 3. So likewise, I mean, with all the other questions that we've looked at today, and previous lessons, we've looked at sketching a graph, which is so important. So this graph would be looking at 3, negative 3, negative 3, and 3, which is going to be a circle. Okay, so that's what the function looks like. Okay, it's a circle. Now, it says that we are rotating this about the x-axis, which means that we're here and we're rotating it around that way. Okay, which basically means if I'm spinning it around that way, what's going to happen is that circular disc that we were talking about before that gets created is sort of that direction, because that's the axis that it's being rotated around. If it was rotating about the y-axis, it means it would be spinning around that direction. Okay. Again, when you're trying to figure out where it's spinning, think about find which axis it's spinning on. Put your arm as the x-axis, and you can watch it going around that arm. Okay, and when it goes around that arm, that hard. I was actually trying to do it and show you with my arm, but I forgot that my arm is not being filmed. That's your arm here. Okay, and this is going around it, as you can sort of see there. Okay, so that's where it's being rotated around. So how do we start this question? Well, we've got my little diagram here. So what I'm going to start by writing out is the rule for the volume. And we know it's about the x-axis. So the volume is pi times the integral, and that's about the x-axis, so it's y squared dx. Okay, so it's not, normally we do y dx, okay, but now we're doing y squared dx. Very similar to what we've been doing previously, okay, it's y squared dx and there's a pi at the front. So what we need to figure out is an expression of our curve in terms of what y squared is. So we've currently got x squared plus y squared equals 9. I'm going to rearrange that, make it y squared equals 9, take away x squared. So now all I need to do is put that in as the integral of 9 take away x squared dx. Okay, and you'll see that once you get that part, it's going to be nice and straightforward after that. So we're going to take the integral of 9 minus x squared. Now you notice I don't have a b and a there, so let's have a look. We've got a b and an a, so we've got 3 and 1. So I can put those in there. So let's now integrate 9x minus x cubed over 3, and we're looking at 3 and 1. And now it's pretty much exactly what you've been doing previously, but except I've got this pi at the front. So we've got 9 times 3, which is 27, minus 3 cubed, which is 27 divided by 3, which is 9, minus, and then put the 1 in there, 9 times 1 is 9, minus 1/3. Now notice that this pi is out the front of that whole thing. Alright, so I need to make sure I keep it there, and then I simply put that in my calculator, that part of it, 27 take away 9, etc. And then what I'll get is 28 over 3 times pi units squared. Or you get pi times 28 over 3, which is 28 pi over 3 units squared. If you want, so it should be units cubed, shouldn't it? Not squared, so my bad there. You can put that as an improper fraction if you wish as well, but I'll say as a mixed number, but I'll leave it like that there. So again, all I've done there is I've drawn a nice little diagram. I'm looking at the parts 3 and 1. All right, that section there. And what I'm actually doing here is finding the volume throughout that whole thing there. Okay, that sort of semi-sphere. What parts are important to remember here? Well, that formula is exceptionally important. Okay, it's the same as what you've been doing your integral of y dx, except instead of putting your y equals here, we're making it y squared, and make sure we get a pi at the front. Okay, let's have a look at the next question. Find the volume of the solid formed when the line y equals 3x minus 2 is rotated about the x-axis from x is 1 to x is 2. Alright, so let's come up with a little diagram. So 3x minus 2, well that means I'm going to be going through negative 2 here. Draw my graph. Okay, so that's y equals 3x minus 2. We're looking from the points 1 and 2, so I wonder what this coordinate here is going to be. So when y equals 0, x minus 2, 3x equals 2, so x equals 2/3. Alright, that will probably be important for us. Well, it might not be that important. That's 2/3. That means that 1's here, 2's here. Okay. So I'm looking for those regions here. Now, remember, I'm not finding the area. If I was finding the area underneath that curve between those 2 points, it'd just be the integral of 3x minus 2 dx. But what we're looking for is the volume, which we know as pi times integral of whatever y squared is dx. Okay. Now, it's rotated about the x-axis again. All right. So basically, what's happening here is this line is being rotated around. Now, if this gets rotated around, what's going to happen is this. It's sort of going all the way around. It's creating this cone as it's being rotated around. All right, we've got this little disc here, and we're looking at the volume inside there. All right. Okay, so how do we do this? Well, the volume is equal to pi times the integral of whatever y squared is going to be. Now, we don't have y squared, we've got y. So what we need to do to get y squared, we need to square this. So let's square that. We're going to get 3x minus 2 all squared dx. Now, what we can then go forward, if you would like to expand that and make it 9x squared minus 12x plus 4 and then integrate from there, you certainly can. I'm going to use a chain rule for this one. But we've got pi outside of, now, I'm going to take this one and do 3x minus 2 to the power of 3 over 3 times, now differentiate that term there, we get 3 in the middle. Now I've got 1 and 2 here and go from there. Again, you could have integrated that by expanding first if you wish, but I just use a chain method for a bit of review of that rule. Okay, so now it's a bit more challenging, I guess, for the substitution part of it, but it will be okay. So pi times, now remember, it's going to be times the whole lot, so let's put it in. 3 times 2 is 6, 6 minus 2 is 4, 4 cubed is going to be 64 over 9 minus 3 times 2 is 6 minus 2 is 4. Oh, actually, we just did that one, sorry. 3 times 1 is 3. 3 minus 2 is 1. 1 cubed is 1 over 9. And again, look, I skipped some of those steps there. You can certainly do your substitution and use your calculator that way. If I do all that there, we should come up with an answer of thereabouts 7 pi, and it's volume, so it should be units cubed. Okay, so I'm just going to recap that question there. So what we did there with that question, we drew the line of y equals 3x minus 2. I showed that it rotated around that x-axis, okay, hence why we had this other line going through here. I looked at, put my points 1 and 2, they are my limitations there, or your intervals, and then I applied it to the rule, okay, and it was about the x-axis, so we're looking for y squared dx. Once I've did that, integrated as we normally would do, and got my answer for the volume. Okay. Not particularly easy, is it? It does get easier though as you go through more questions. Okay, let's do a y-axis one. Find the volume of a solid formed when the curve y equals x squared minus 1 is rotated about the y-axis this time. Okay, so let's see what the differences are when we do this diagram. So we've got x squared minus 1. Well, hopefully you recognize that the graph looks something like this. Well, that's negative 1 there. Now, if it's rotating around the y-axis, it means it's spinning around this y-axis here, which means that my disk, well, let's do negative 1 and to positive 3, we'll put 3 here, means that it's spinning around this point here. Okay, and then it's spinning around this bottom point here, which is that sort of bottom bit there. So that's where it's spinning around. Okay, so you can see that it's going around that actual y-axis, and that's, I guess, like the center pole. So what's the difference between this question? Well, it's y-axis, so it means that we're using the rule volume equals pi times integral of x squared dy. Okay, not y squared dx, it's x squared dy. It's kind of like, I guess, when you were doing the integral of or the area when we were doing it with bound by the y-axis, we were putting x is equal to instead of y is equal to. Similar thing, we put it as x is equal to, but it needs to be x squared. So it's actually pretty straightforward. It's just basically doing your pi times your area, okay, but making sure that we have squared that value. So let's have a look at this. Volume equals pi times, we now need to, or we actually need to know what this is going to be, don't we? So I'm going to do that. My apologies. So I'm going to put the integral of our x squared is, now we've currently got y equals x squared minus 1. So let's plus the 1 across there. I've got x squared is equal to, so it's y plus 1 dy. Alright, so now we've got that. Oh, hold on, we've got, put my 3 and my negative 1 there. We can now scroll down and we can move on from that. So let's integrate. Volume equals, now I need to put my pi outside. We've got y squared over 2 plus y, and we've got 3 and negative 1 there. So now what we can do is substitute. Volume equals pi times 3 squared is 9 over 2 plus 3 minus negative 1 squared is 1 over 2 minus 1. Now put that in my calculator. Obviously we've got pi at the front. Chuck that in. We're going to come up with 8. So therefore the volume equals 8 pi units cubed. Okay. Look, again, I'll just recap finally. That question there, we're rotating about the y-axis. Okay, so we're using that second form of our formula. Volume equals pi times the integral of x squared dy, making sure that we need to have our equation in the form of x squared equals, so we can substitute that into it. Once we've done that, okay, we can integrate just as you would normally do, making sure you got the pi out the front. This isn't particularly easy. It's certainly different. I'm certainly sure that I've confused you, no doubt, and I'll probably be making another video trying to clear things up a little bit. But hopefully that made just a little bit of sense and gave you enough to go on to work on exercise 3.9 from the Red Book on page 116 for my 2-unit class. But certainly if you're having any more issues or that was as clear as mud, let me know and I'll try to tighten this episode up a bit more. Cheers, guys.